So what might cause systematic error? One source is bias. Bias is a really fun topic to learn about and probably a funner topic to talk about. Understanding the different types of bias that can occur in a study is moderately high yield and worth reviewing. Bias is defined as the situation in which an outcome is systematically favored over another. It therefore causes systematic error. Alright, let's look alive with a flash quiz. Do you recall what systematic errors reduce? Systematic errors reduce the accuracy of a study. Okay, let's start with bias that can occur when recruiting patients for your study. Selection bias is the non-random assignment of subjects to the study groups. For example, selection bias can occur if the patients themselves decide which group to enter into. Thus, each group is not a representative sample. There are a few more specific examples of selection bias, such as Bergson's bias. In this type of bias, the study population is selected from a hospital. So clearly, people in the hospital are not a healthy population compared to the general population. Another example of a study population that is subject to Bergson's bias is called the healthy worker effect, where people are healthier than normal. For example, if you were doing an orthopedic study on ACL repairs in competitive athletes. Can you think of a few other examples? Something like loss to follow-up or non-response bias. These are also common causes of selection bias in many studies. In each of these situations, the patients in each group render the group non-random and thus non-generalizable. Let me illustrate this for you a bit more. Let's say you're running an intensive weight loss and diet program. At the start, you've enrolled a group of people. They all start your weight loss plan. You make them exercise, and you make them diet, but some of these people won't make it to the end of your plan, either because they can't maintain it, or they don't think that the plan is working, or maybe some other reason. At the end of your trial, you've got people who both lost weight successfully and some people who didn't budge on weight loss. However, you've lost all of these people who may not have benefited from the exercise and the diet either, and so you've excluded all of these data points that would influence your results. Let's talk now about bias that occurs while you're running your study. Recall bias is when the knowledge that a disorder is present affects recall by subjects. For example, if patients are asked about past behaviors like smoking that may have had a negative effect, such as during pregnancy, the patients may not remember or report these behaviors accurately. Hence, recall bias is common in retrospective studies. Sometimes, if you can catch your population of interest close to the occurrence of the events, you can decrease recall bias because your population has less time to mull over their situation and try to make sense of it. Measurement bias happens when information is gathered in a way that distorts it. For example, my GPS on my phone always overestimates the distance I've run, but it keeps time perfectly. The result is that I think I'm running faster miles than I actually am. The only way to combat this is to standardize the method of data collection. Procedure bias occurs when subjects in different groups are not treated the same. For instance, when more attention is paid to the treatment group, leading to greater compliance with treatment. How could this be avoided? Good, yeah, by blinding the researchers and doctors administering the treatment. The observer expectancy bias occurs when a researcher's belief in the efficacy of a treatment changes the outcome of that treatment. This is a form of observer bias and can be avoided by having an independent observer interpret experimental outcomes. What kind of blinding is this? That's right, double-blinded or even triple-blinded. Confounding bias occurs with two closely associated factors, when the effect of one factor distorts or confuses the effect of the other. This bias occurs during interpretation of data. Here, the effects of extraneous factors muddle the exposure-disease relationship. Confounding bias can be present by matching controls to cases so that they have all the same characteristics except for the factor of interest. Lead time bias occurs when early detection is confused with an increase in survival. This type of bias is commonly seen with improved screening. The natural history of the disease is not changed, but early detection makes it appear as though survival is increased. With this type of bias, think about screening tests, such as those for cancer. Using placebo, blinding, or crossover studies can aid in decreasing bias. Crossover studies are those in which each subject acts as their own control. This means that if Group 1 receives a drug and Group 2 receives placebo, at some later point in the study, Group 2 would receive the drug and Group 1 would receive the placebo. In this way, both Group 1 and Group 2 act as their own controls, and many different forms of bias are eliminated in this manner. Randomization is very effective at reducing selection bias and confounding bias. And finally, matching subjects so that the groups being compared only differ by one important parameter is a good way to reduce confounding bias. It can be hard to keep track of so many different types of biases, so let's try an example question. Clinical researcher wants to determine how frequently primary care physicians ask a patient, "Is there anything else you would like to talk to me about?" at the end of a visit. She designs a study in which patients are asked to fill out a questionnaire immediately upon leaving a doctor's office. In order to conduct this study, the researcher describes the research study to 20 different physicians and asks for permission to give questionnaires to their patients over a 1-month period. What's a potential problem with this study? The subjects in this study are physicians, but in order to conduct the study, the researcher has to describe the study to the subjects. Awareness of the study will likely affect physician behavior and therefore reduce the validity of the study results. In other words, the physicians will likely ask the question of interest more often during the study because they know that that's what's being measured. This type of bias is known as the Hawthorne effect. Okay, up for one more? You want to know if heavy alcohol consumption increases the risk of bladder cancer. You conduct a prospective cohort study comparing drinkers to non-drinkers and obtain a relative risk of 2.3 with a p-value of less than 0.01. Are you satisfied that you have demonstrated a causal linkage between drinking and bladder cancer? What type of bias may be at work here? This is a classic case of confounding bias. Since smoking is linked to both the independent variable drinking status and dependent variable, bladder cancer in our study, it may explain some or all of the association we observe between drinking and bladder cancer. Now we will discuss various terms that are used to describe statistical distributions. Let's start with the basics. There are several measures of central tendency. These are likely familiar to you: the mean, the median, and the mode. The mean is simply an average, or the sum of all values in a set divided by the total number of values. The median, on the other hand, is the middle value of a list of data when it's been sorted from least to greatest. And finally, the mode is the most common value. Which of these numbers is most affected by outliers? The mean. And which is least affected by outliers? That's right, the mode. Which of these stats would be best discovered by charting a histogram? That's right, the mode. What would you do if you were calculating the median and you had an even list of numbers? As in, the number of numbers in the numerical set was even. Right, you would take the average of the middle two numbers. Now we will discuss various terms that are used to describe statistical distributions. The normal, or Gaussian statistical distribution, is bell-shaped, and the mean, median, and mode are all equal. The standard deviation, denoted by a lowercase Greek letter sigma, describes the spread of the data about the mean. How would the standard deviation be affected in a very precise test? It would be decreased, since the variation of the data is lower, and the bell curve would be skinnier. However, a precise test may still not be accurate, which would look like this, where the spread is low, but the result doesn't reflect the true population. As shown in this diagram, for normally distributed data, 68% of the data falls within one standard deviation of the mean, 95% of the data falls within two standard deviations of the mean, and 99.7% of the data falls within 3 standard deviations of the mean. As an example, if the mean systolic blood pressure of a population is 130, with a standard deviation of 10, how many of a 100-member cohort will have blood pressures greater than 140, assuming a normal Gaussian distribution? We can calculate that number as follows. 140 is one standard deviation above the mean. And we know that 68% of the cohort, or 68 members, will have values within plus or minus one standard deviation of the mean. Thus, 32 members have values above 140, or below 120. By symmetry, we can conclude that 16 members would have systolic blood pressures greater than 140, and 16 members will have systolic blood pressures less than 120. The standard error of the mean, or SEM, is defined as the standard deviation divided by the square root of the sample size. Understanding how SEM differs from standard deviation would be a little tricky. Let's assume that you have a population of interest, but you can't measure everybody in the population. So what do? You select a random sample. It's a certain size, and you assume that it's representative of the population. Measure them, and then find the sample mean. Put these people back into the population. Then, take another random sample. It's the same size, calculate their sample mean. You can repeat this process as many times as you want. How precisely do these sample means reflect the true population mean? That's where SEM comes into play. The SEM measures the spread of the sample means about the population mean. Recall that SEM is the standard deviation divided by the square root of the sample size. Therefore, as the sample size increases, SEM decreases. Does this make sense? It should, because it tells us that as the sample size gets larger, the sample means become a better estimate of the true population mean. Is the standard deviation affected by sample size? No. The sample size has no effect on the standard deviation, only on SEM. What is the effect of the sample size on the SEM? That's right, SEM decreases as the sample size increases. Shifting gears now, let's talk about deviations from the normal distribution. Take a look at this bimodal distribution. What do you think would cause something like this? That's right, two different populations. You might think of something like this when considering onset of certain cancers or suicide rates by age. Shifting gears now, let's talk about deviations from the normal distribution. A positive skew is a distribution that occurs when there is asymmetry with the tail lying on the right. In these distributions, the mean is usually greater than the median, which in turn is typically greater than the mode. A negative skew in a distribution occurs when there is asymmetry with the tail lying on the left. In these distributions, the mean is usually less than the median, which is typically less than the mode. What term is best used for a skew distribution? In both positive and negative skew distributions, the median is a better measure of the central tendency than either the mean or the mode. Also, in all distributions, the mode is the most resistant to outliers in the samples, whereas the mean, standard deviation, variance, and range of the distribution are all very sensitive to outliers. The median is only slightly more affected by outliers than the mode. If the reasons for these statements are not immediately clear, spend some time thinking about them based on the definitions of these statistical terms. Let's do a flash quiz. Is this a positive or a negative skew? It's positive. The tail is on the right. Let's try a practice question now. Hospitalized patient has 10 consecutive measurements of their systolic blood pressure. Suppose that the largest pressure measured is 125 and the lowest pressure is measured at 115. The next measurement is 180. Which metric is most likely to remain unchanged? Standard deviation, standard error, mean, median, or mode? The mode, which is the most frequently observed data point, is the most resistant to outliers. All of the other metrics are more sensitive to outliers.